Hello everyone and welcome to the tutorial series on LLM fine-tuning for anti-tracking in web browsers. In the previous session, we learned how to create data that we will use to train our model. In today's session, we are now going to take this data, use a pre-trained LLM, and fine-tune that model to detect trackers. This is Dr. Humera, and I am your data and AI mentor. I will take you through the LLM fine-tuning, so let's get started. In order to understand what model training here implies, let's have a look at what are the steps that we will be taking. It's important to note a little bit of terminology. Although the section that you are seeing here is called as training the model, but in reality, we are not per se training a model, rather we are taking a pre-trained model and fine-tuning that. So it's better to call this as fine-tuning the model rather than training the model. And let me explain. So first of all, how we are going to work on it. In the data repository that you have already downloaded from GitHub, you have a script called as train_model.py. This is the function, this is the script that we are going to use today. Here, we will use a pre-trained model called DistilBERT base uncased as our base LLM. We will fine-tune this model and then use the ground truth data that we generated in the previous session to train or update our model. The fine-tuned model, after being trained or fine-tuned, will be saved in a folder called final_model. And the code will end by evaluating the model and generating some stats. In order to run this function or in order to run this code, you need to go to your terminal and simply invoke the function. I keep on calling this the function, but it's the script. Invoke it by calling python train_model.py. Now, a few things to note. Let's have a look at our code before proceeding. First thing, why we are going for a DistilBERT base uncased, and what does that imply? To understand this, there are a number of pre-trained models available online. BERT being one of the most popular ones, which is available from Google. Now, from the BERT's family, there are many variations that were developed afterwards. These were coming from different organizations like Hugging Face, Huawei, also from Google, and they have a few major differences. Mostly, the difference is in the size of the model, and that size indicates how the performance will be affected and how the training times will be impacted. There are many other parameters as well that will be impacted that you can see here on the left, the features. But for us, the most important ones are these: how much space or memory a model is taking, how much time it is taking for being fine-tuned or trained, and how much is the impact on the performance. If we look at the BERT base uncased, uncased represents its case insensitive, which means a capital alphabet and a small alphabet is treated as the same. This is actually good for our URL-based tracking detection because http://whatever.com written in capitals versus written in small alphabets is similar. So we are going for the uncased version. Now there is an even more smaller variant which is DistilBERT. And this is a summarized version of BERT. This is a smaller version of BERT. If we go through the details of the comparison between BERT, BERT uncased, and the DistilBERT base uncased, again focusing on the important factors which were, for example, the model size. As you can see in the column model size, in the row model size, the BERT base uncased has 110 parameters, 110 million parameters. On the other hand side, the DistilBERT has only 66 million parameters. which makes DistilBERT 40% smaller than the base one. If we look at the memory consumption, the memory usage, again for BERT base uncased, it's higher, and the DistilBERT base uncased, it's 40% lower than the BERT base. The second thing which is important for us is how long does it take to fine tune the model. If we look at the parameter speed, then the BERT base uncased is the same as the BERT, the reference one. On the other hand side, the DistilBERT is 1.6 times faster. So being smaller, it gives the advantage that there are less number of parameters to be trained or calculated, and so it takes a less amount of time to be trained. So it's kind of a win-win situation. But what's the catch? The catch is in performance. So if we look at the performance parameter, the BERT base uncased is at 100% because that's the reference. And we see that the DistilBERT base uncased is retaining 97% of the BERT base performance, which means that 40% of memory is saved, 40% of time is saved, but only 3% of performance is being lost. So it's not a bad trade-off for us. By the way, there are many more variations of this model as well. If you want, you can explore further, for example, the tiny BERT or the mobile BERT, which are even smaller and faster. If we quickly compare the size of tiny BERT with DistilBERT and mobile BERT, you can see that the model size is only 14.5 million parameters for tiny BERT and 25.3 million parameters for mobile BERT. They are respectively 87% and 77% smaller compared to the BERT base uncased, which was our reference. Similarly, if we go for speed, then tiny BERT is 9.4 times faster than the BERT base model, and the mobile BERT is 5.5 times faster than the base model. When it comes to performance, tiny BERT loses only 4% of the performance of BERT, and mobile BERT is claimed to retain the 100% of performance. Which means when you want to run these models on smaller machines, when you are very short on resources, like you are on your mobile, then in this case, it's better to use tiny or mobile BERT. For here, right now we are going for DistilBERT, which is actually a good trade-off between the size, speed, and performance. But it's totally up to you whichever you want to go for. So how do we proceed? Going back to what we just saw, we will use DistilBERT case uncased for our purposes. You are free to choose whichever model you want. Then you need to have the training underscore data.csv. This is the file that we created in our last session. Let's have a quick look on that. So this is the data that we created in the previous session, and it has two columns. The first one is representing the URLs, and the second one is representing a label, which is 0 if the URL is not a tracker, and 1 if it is a tracker. Let's have a look at the code that we will be using for training. So let's go to the train underscore model.py script and have a look at how the different pre-loading of the model is happening, how the fine-tuning is happening, what are the things that we can control, and what are the things that we already have available. So in this code, you can see, if you scroll a little below, then first of all, it's checked whether you have a GPU installed or not. GPUs or CUDA makes things a lot faster than CPU, like 100 of times faster. So for example, if for a typical 1000 data points data set. On a CPU, it might take at least half an hour, 1 hour to train or fine tune the model. If you have a GPU installed, then it will take only 2 or 3 minutes. And as you can imagine, as the number of data points increase, as you change your parameters, CPU will take even longer, like several hours or even days to train a model. In fact, sometimes having a CPU makes it almost impossible to work on such models because the training time or the fine tuning time is simply too much. But in case you don't have a GPU available on your machine, which is totally normal, then this code will work on CPU as well. It will take a bit longer, but it will work. Here we have specified the distilbert dash base dash uncased. As I told you, you can here use the tinybird as well. Just check out what are the standard names available by the providers and use the exact name over here. Then we are specifying the maximum length of our input. So since our input is a URL, the tracker URL, we need to specify how many characters do we want to have. 64 is a good enough character length. So it will include your domain name, your protocol, and a lot of query parameters as well. In general, 64 is one of the maximum lengths of the URL. We will see this in optimization, but for you to know, if you want to play around, you can try out different lengths of the URLs as well. Of course, if you just take a very small length of URL, let's say 4, it will always cut your URL at HTTP, and that doesn't make sense. But if you, for example, try maximum length to be 32 or 16 or 48, you might be able to play around with different parameters, and you might be able to have a different result based on the precision and recall. Changing of all these parameters which we are looking at right now, like maximum length, batch size, etc., that is part of your fine-tuning the LLM. So what we are doing right now, we have taken this distilbert base uncased as the pre-trained model, and now we are fine-tuning the parameters in order to retrain it with additional data. Batch size, if your device is CPU, then the number of elements that you want to hand over should be less because CPU can't handle much more. But if you have a CUDA installed, if you have GPU, then you can work with larger batch sizes of data points, which is 32 in this case. Similarly, how much precision do you want to have for your floating point numbers? If you don't have much processing power for CPU, you do not go for higher level of floating point precision, and if you have the capacity, then you keep it. Of course, if you want to run this code without making any changes, it should run out of the box. So this boilerplate code has been written in a way so that you don't have to make any changes, but it's great idea to be able to control these parameters and try them out. Now we have a class. This class actually takes the data from the data set, the training underscore data.csv, and converts it into a form so that it can be given to the model for training. Here you can see that the ground truth data will be read. In the previous session, we stored it in the data folder under training underscore data.csv. You can read it from here. As for any machine learning project, you need to have a good split between the training data and the test data, so that whatever model is being trained, whatever training is happening, we are able to evaluate our model on the basis of some test data, some data which the model has never seen before. And for this reason, the splitting of training and testing data is happening using one of the predefined functions from scikit-learn, the train underscore test underscore split. Here you can see that 20% of the data, because of point 2, 20% of the data is being taken as the test data, and 80% of the data is used for training. A very important concept for training or fine-tuning your BERT model is the concept of tokenizer. BERT is coming from a family of machine learning, which is transformers. We are not going into the details of transformer based machine learning or deep learning, but it's good to know that transformers allow training of the system in a way that is fast and that allows longer stream of text data to be decoded and encoded properly. And for this, whatever stream of data is there has to be converted into tokens. And these tokens are used in further training. Since BERT is an already trained model, it's a pre-trained model, so we have the tokens available for BERT. When we download the pre-trained model DistilBERT, then the tokens for DistilBERT will also be downloaded. And this is what we are doing here. We are getting the tokenizer. This is done by using the transformers library. And here the auto tokenizer from pre-trained model name is used. So our model DistilBERT is used, and here the tokenizers, the tokens are downloaded, and then the model is downloaded as well. So again, from underscore pre-trained is a built-in function from the transformers class. We can have a look at this, the auto model for sequence classification in the beginning. This is coming from the transformers class. Also the auto tokenizer is coming from the transformers class. Both of them are downloaded and then used for fine-tuning. Now let's specify some training parameters. We have already specified that we will have the maximum length of 64. That's what we are specifying for our encodings. If a variable, if a URL is smaller than 64, then do we need to just cut off the URL, or do we want to pad it with additional parameters so that everything is of the same length? Here we are specifying that the padding should make everything of maximum length. This will ensure that all our data inputs are of the same length. If something is longer than 64 characters, then it will be cut at 64. If something is shorter than 64 characters, then additional blank spaces or nulls or zeros will be embedded to make it 64. This is also part of the fine-tuning. You can specify that you don't want to have a maximum length, rather you want to keep it dynamic. This will help you in controlling the size of your input, and that will influence the quality or the metrics that you are going to measure. You apply the same formulation for training encodings and the test encodings. Then you prepare the trained data set and the test data set. For this, the class that we just saw above, that will be used for conversion of URLs into tensors, which will be used for training. What other training fine-tuning can you do? So it's important to know that where will the results of the training stored. So the model will be downloaded, it will be fine-tuned, further trained, and then stored somewhere. Where will we store these this model and its related parameters? It will be under output underscore directory, which is results. This is where the results will be stored. Then the number of training epochs, we are going for 2. Again, you can fine tune this parameter. You can have lesser or more. If you'll have lesser parameter, a lesser number of epochs, that will train the model for 1 cycle and then stop. It's quite possible that the 1 cycle is not enough for training the model, and it might not give you good results. Too many cycles, too many epochs might result in overfitting and or even pause in the training without any further progress, and it will just take more time. So 2 is a good number to start with. Then you specify how many batch size. We specified in the beginning that for CPU we'll go for 8. And then you can specify the learning rate, which we are going with 3 exponential minus 5. You can increase or decrease if you want to make things faster or slower and more fine controlled or coarse grained. Then you can specify the weight decay, which here is 0.01. Do you want to evaluate your model while it is being trained? If yes, after how many steps do you want to train it? Here we are going for 200 steps. So evaluation will happen after every 200 steps uh, as long as the training is going on. And then which kind of optimizer do we want to use? We are going for CPU because, sorry, for CPU, we are going for Adam W underscore torch because that's a safe optimizer that works on CPU. Else you can go for Adam W underscore apex underscore fuse. This is a faster one, works better with GPUs, and so on and so forth. So changing all of these parameters is considered as fine tuning of your model, and once you have specified all of this, you are then ready to go. Then we have some functions for computing metrics. We will have a look at this later on. This will actually keep on checking the parameters which are important for us to measure, like accuracy, precision, recall, F1, and so on and so forth. Once we have specified all the parameters, now we are ready to start training. So here we specify that this is the model that we will use, the DistilBERT. All the training arguments which we have specified above will be used as the arguments. We have specified what is the train data, what is the test data, and which metrics do we want to compute. And then by a single line of code, trainer.train, we are calling the built-in function train from the transformers library. This is the longest step over here. This will take, depending on if you have a CPU, if you have a GPU, how many data points do you have, how much is your learning rate, are you going very fine-tuned, are you going very coarse-grained. Depending on all these parameters, it will take some time to train your model, and once that's done, then the model will be saved in the final underscore model. Also, the tokenizer will be saved, and then we will start with some testing. But before we go ahead with testing, let's first start running our function, not the function, the script, and let's start training. So for this, let's go to our terminal. Once again, we need to be in our right folder, the LLM-NT-track directory, and our virtual environment needs to be activated. Here we can run the program python train underscore model.py. It will start initializing. It will download the pre-trained model, the distilled base uncased model. It will look at the training data that we have under the training underscore data.csv file. It will download the tokenizer. After doing all the initialization, it will start execution. So now it has read the ground truth data, it has split the train and test data set, it is getting the tokenizer, it's getting the model, and now it has started training. As we can see here, based on our data points, the 1000 data points that we generated, 2 epochs, based on the learning rate, it is going to take 200 steps, and right now we are at step number 2. So let's give it some time and it will continue to train. All right, training has completed, so let's have a look at what do we have on our terminal. So if we scroll a little bit back up, the training was completed, which means the fine-tuning was completed based on the existing pre-trained distilled BERT model and the data points that we gave via training underscore data.csv. Once the model was trained, it was saved in a final model, and the fine-tuned tokenizer was saved as well. Let's go to our Finder and check these files out. Here the model and the related files are stored in the final underscore model folder. We browse to it and we can see that we have some configuration files. We have the model, we have the tokenizers, and everything that we need to later on use this model for making inference. Coming back to our terminal, after getting done with our training or fine-tuning, we went ahead and did some evaluation. For this, we specified in our code to check for some URLs if they are tracker or not. So as we can see here, the first tracker URL, the first URL is cdnshopify.com, and the model has predicted that it has a very low probability that this is a tracker. It's only 0.2%. And so on and so forth. For all these trackers, the model basically recommended that these are trackers with very low percentage. This doesn't look very correct. Let's quickly have a look at our code and see what did we actually give there. So in our script, we can see that yes, a few of these URLs were indeed not trackers. So for example, these 3 parameters were not trackers, but this Wikipedia page was a tracker, and here you can see that we have ads as a label here as well. Also, this YouTube page or the YouTube URL also had ads, which is also regarded as a tracker in our ground truth. However, our model said that these all are non-trackers. We will need to explore why we are getting this output. So we can see that we have for the first 3, the tracker prediction, the tracker probability is indeed very low, 0.2, 0.2, 0.2. For the last 2, it's a bit more, like 6.6% and 3.4%, but that's still very low to be regarded as actually a tracker. Another thing which, another kind of evaluation which our script did was some kind of bulk stats generation. So what we did is, remember we had this 20 and 80% of split. The model then evaluated the data on the rest of 20% of the data points. So 80% was used for the model training, the fine tuning, and now we are using those 20% of the data points to see how well the model has been trained. And here the results are actually very opposite. Here we have a validation accuracy of 98%, that's a lot, and a precision of 100%, which means no wrong answers, everything is regarded correctly. There is a little bit of a drop in the recall, which is still quite high, 94.29%. Our F1 score is 97%. And here we have some more details that the true positives are 66, which is correctly identified trackers. False positives is 0, which means non-trackers incorrectly flagged as tracker. This never happened. Then 130 true negative, which means anything which was a non-tracker, it was correctly identified as a non-tracker. And then these 4 trackers were missed, so there were 4 false negatives. So, although the results are too good to be true, but this is what our evaluation shows us. And that's why it's important that we do some independent testing as well. So, going back to our next steps, I encourage you to try out some further things and test your model, train your model with other parameters. If you want to play around more with the model training, you can try out other variations of BERT's model. You can try out the tiny BERT, you can try out mobile BERT, or a bigger variation of BERT if you have the capacity to do that in terms of CPU or GPU processing power. You can adjust the epochs, learning rate, training parameters. Try having, instead of two, 5 epochs. It will take longer, but it might give you some better performance, or increase or decrease the learning rate. Fine tune your parameters. You can also have more training data. Perhaps 1000 training data points was too little to train this model. Go for 5,000, 10,000, 15,000. Again, it will take way longer than just 1000 data points, but if you have the capacity, do that. And you can pick more trackers for sample evaluation. See which are the known trackers and if your model is able to identify those. For now, we are going to do some more testing. And for model testing, we will go ahead, generate more data using the data generator .py, and then run another script called test underscore model.py. Here is what we need to do. So as you can see that by default, the train model py is doing some kind of testing. That was the testing which was given as part of the training model. And we saw that although the results are not that great when we are looking at individual inferencing, but the overall metrics are very high, much more high than expected. 100% precision shows something is really off. It's quite possible that the training and testing data, which was created as part of the training file, they were very similar to each other, and that's why the model actually recognized everything without really generalizing. And that's why we need to do some explicit testing. So we need to take one step back. We need to pull out our data generator py file again and run it for creating some test data. Feel free to add more domain names, change the parameters over there, and create more data out of it. If you want to recall how to do it, go back to the previous session where we looked at in detail how to how to use the data generator.py to create the data. Now let's say you have the testing data.csv. You can now run the script called test underscore model.py. This generates the classification labels as tracker, no tracker for a list of URLs specified in the code, and it will also generate the stats. Let's have a look at how the script looks like. For this, let's have a look at the boilerplate code that is given to us in the GitHub repository. It's test underscore model. So what we do here is load the pre-trained model, which was just trained and stored in the final model. We use that model, and along with that, you saw that the tokens are also saved. So the tokens are also loaded from our file and from our path. Next, we open the file which is in the data folder which you created using data generator.py. And then you use this pre-trained model which was further fine-tuned along with the test data to evaluate the model. What is important for you to know is that you can do evaluation in two ways. And for that, we scroll to the bottom of the page. Here you can specify manually a few URLs that you would like to test. So here we are giving again some URLs for which we know some of them are trackers and some of them are not trackers. And then here is the test for bulk URLs. So this will create inferences for the trackers or non-tracking URLs that we manually specify. And we are going to test these individual URLs. And then afterwards, we are going to evaluate the model using the model which has been trained in the previous step, using the data which we have already generated. So now let's go ahead and check this out. To execute, we use the Python command test underscore model dot py. It will take a few seconds or a few minutes to load the model from our folder final model. It will open the data, the test data, and now it is testing the individual URLs. So here we can see a few results if I scroll back up. So for example, for the first one, it is 99% confident that it's a non-tracker. That's correct, that's good. Similarly, for the Netflix one, we also see that it's 99.7% confident that it's a non-tracker. That's good. The third one for CDN, Shopify, this is also predicted as a non-tracker. Then comes another one, Wikipedia page. This is ads. This is a miss here because again here this is regarded as a non-tracker with a confidence of 93.36%, which is wrong. This is actually an ad here, as we can see, but our model is predicting this as well as the non-tracker. And here as well, we have a wrong prediction. This has clearly ads in its parameters, but this is regarded as a non-tracker. So again, just like in the previous step, we can see that mostly we are more biased towards regarding everything as a non-tracker. But let's see how are our results. So now it is processing the URLs. Our data set has 1000 URLs. Now it went ahead and right now we are at 47%. This many URLs have been tested. Let's wait for it to complete testing and then we will see how our results look like. Interesting results we have here. For our model, accuracy is coming out to be as before 98%, precision is 98%, at least it's not 100% now. The recall is 96, 97, 96.5%, and F1 score is 97%. We can see that mostly our identified trackers were correct, which means that they were true positives. There were a few false positives as well, where non-trackers were flagged as trackers. Then we have correctly identified non-trackers and we have trackers missed. And the above trackers which we noticed, the problems that we noticed over here, that was basically this specific case where we had trackers which were missed and regarded as non-trackers. But to begin with, having 97% F1 score, that's not really bad. I actually like my results. And here you can see that there were, in this test data set, we had 350 trackers and 650 non-trackers. And that was the distribution, so kind of evenly distributed with respect to our training data as well. This is indeed exciting, isn't it? Like, no matter what your results are, whether they were 90% plus or they were less than 30%, it doesn't matter. What matters is that what you did in so far is you have taken a pre trained LLM, Distilbert in our case, you generated your own data, which was a huge representation of how tracking URLs and legitimate URLs look like. And you use this generated data to fine tune and train your model. And this model now gives you such a high precision, a high recall, and such a good amount of F1 score. So you were able to take an LLM and fine tune it from scratch. This is really exciting. It's not as difficult as it sounds. Like hyperparameter tuning sounds like something which is really specific to some specific kind of people, but no, it's not true. If you want to do it, you can do it. In fact, now I have a challenge for you. I would love you to be part of our competition, a leaderboard, part of our leaderboard, where you can send over your results, your trained results to us, and let's see if you make it to the top of the leaderboard. So here's how it goes. Do your training, do your testing. When you are done with testing of your model, you will have some accuracy metric, precision metric, recall, and F1 score. Collect all the information and send it over to the email ID webmail@digitalmunich.com. Please send also your model that you have, specify the model that you have used. You don't need to send over the model, just tell us which one did you use, and send over a copy of your train_model.py. If you want, you can include a display name, your GitHub repositories ID, and a display picture. And let's see if you make it to the top of the leaderboard for this LLM fine-tuning project. With this, we are at the end of our today's session, LLM fine-tuning for anti-tracking in web browsers. We are done with our machine learning part. In the next session, we are going to set up a server, and using a browser extension, we are going to call our machine learning model and do inferencing live in servers. Stay tuned and see you in the next session. And needless to say, if you get stuck at any point in time, if you have any questions, if you would like to discuss anything, feel free to reach out. I wish you all the best and see you in the next session. Bye.